Welcome to Monochemistry. In this lesson we're going to learn about the concept of entropy. Entropy is more or less described as the amount of randomness or disorder within a system. However, it is more specifically defined as a measure of the number of ways a system's energy can be arranged. The greater the number of ways the energy can be dispersed throughout a system, the higher the entropy, or the randomness, or the disorder of the system. The fewer number of ways the energy can be arranged, the lower the entropy, the randomness, or the disorder. If we take this example of a small bottle of perfume, in the first scenario, the bottle is enclosed and the particles within the bottle can't get out. However, what happens to the entropy if we open the bottle? As you can see, in this state, there is less randomness. These particles are more ordered, and they're contained within this small space. However, when I open the container, the particles are now free to move about, and they spread their energy throughout a bigger area. Therefore, the entropy is increasing. Now, entropy is denoted by S. S stands for entropy, and delta S stands for the change in entropy. So the change in entropy from here, from situation 1 to situation 2, would end up being greater than 0, because the entropy is increasing. If I was to go the opposite direction, the entropy, of course, would go down. Here are some examples of processes that show an increase in entropy: melting, boiling, and dissolving. All of these processes increase the randomness of the particles and therefore increase the entropy of the system. Standard entropy. Standard entropy, like standard enthalpy, is a particular substance's entropy in a given set of conditions, standard conditions. And it's denoted as follows. Standard entropy, S prime, or change in S prime, if we're talking about change in entropy, and it is measured in joules per Kelvin mole. Okay, so there's a couple of things here. If we're ever dealing with delta H and delta S, which we will be a little bit later on, note that this is in joules, and so we won't be able to we'll have to make some sort of a conversion in order to work with those two values. The other thing you probably noticed is that we have Kelvin down here. Because entropy is dependent on the temperature, the Kelvin becomes a part of it. Let's try an example problem from the textbook. The example problem we're going to try is 18.1. And 18.1 starts on page 807 of your textbook and continues on page 808. However, before we do that, I would like to just mention, overall, the more particles there are after a process, or the more spread out the particles are, the more entropy the system has. So if we do a reaction and we end up with more particles than we had, or we end up with particles that are more spread out, then the entropy is going to increase. The entropy of the system is going to increase. All right, so let's try the sample problem. Okay, so in this question, what we're expected to do is determine if the entropy is increasing or decreasing. So remember, entropy is a measure of the randomness or disorder, or, if you prefer, a measure of the number of ways the energy can be distributed in a system. So let's look at the first one. Part A, the freezing of ethanol. As it says in the textbook, the strategy is this. The sign delta S will be positive if there is an increase in the number of microstates, i.e. the number of places energy can be distributed, and negative if the number of microstates decreases, i.e. the number of energy distribution points decreases. So, in freezing ethanol, we're taking a liquid and we're turning it into a solid. Liquid turning into a solid. Are the particles becoming more or less ordered? Think about in your heads the picture, the model of what a liquid looks like compared to a solid. Which one of those two structures has more order to it? I think you'll agree that the solid has more order to it than a liquid does. Therefore, if we freeze something, the delta S is in fact going to be less than 0. The entropy is going to decrease. However, if we do the opposite, if we evaporate a liquid, if we turn a liquid into a gas, we are in fact increasing the space that the particles take up. The particles are more spread out, and therefore we're increasing the entropy. So the delta S is going to be greater than 0. All right, I want you to pause the video, and I want you to try the other two processes. Turn the video back on when you're ready to see the answers and check your work. Part C, dissolving glucose. If we're dissolving glucose, we're actually increasing the number of places where the energy can be distributed. And therefore, the delta S is going to be greater than 0. However, if we're cooling a gas, remember, gas particles have higher kinetic energies at higher temperatures. So if we cool the gas, the particles are going to slow down and therefore be able to come closer together, or if you prefer, be less spread out. And as such, the entropy of the system is going to be less than 0. Okay, so notice, if the entropy is decreasing, then we're going to end up with a negative value, and that's going to be for this one and this one. If the entropy is increasing, we're going to end up with a positive value, and that's going to be for those two right there. That in a nutshell is what entropy is and how to determine, theoretically speaking, whether or not the entropy level is going up or down in a process. Make sure you bring your questions to class.